Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 8.2, which is going to introduce us to the next geometric idea that we're going to try to measure and understand via integration, which is surface area. This section directly relates back to something we did earlier in Chapter 6. If you remember, back in Chapter 6, we studied solids of revolution, where we took a region or area defined by a curve and revolved it around a given axis, building a three-dimensional shape. In that section, we were interested in measuring the volume of that three-dimensional shape. Here, we're going to be interested in measuring the surface area of a three-dimensional shape. So in other words, our main question for this section is we're going to try to figure out if we can find a way of measuring the surface area of a solid of revolution. So to help us sort of understand this a little bit better, let's go ahead and give ourselves sort of a general diagram and explore this a little bit further. So we'll give ourselves an axis as sort of normal. Let's give ourselves a curve. So there's our curve there. We'll sort of imagine for now that we just got this some arbitrary interval a to b. And for simplicity, we'll go ahead and we'll start by imagining that we're revolving this around the x-axis. So you can imagine that you get that sort of mirror image down here. And that three-dimensional shape is going to be sort of looking something like that. Now, again, back in Chapter 6, what we were interested in is the volume of the shape. So we imagined not just revolving the curve, but also all of the area to make the entire shape here. And so in some ways, if you want to think about it in a very sort of common sense sort of way, in Chapter 6, we were measuring how much stuff could fit into sort of a container like this. Now, we're going to be interested in measuring the surface area of the shape. So again, if you want to think about that in the sort of common sense way, we're now going to be interested in determining the amount of material necessary to build a container that looks like this. So Chapter 6 was volumes. We were trying to figure out how much stuff goes into a container like this. Now we're interested in how much stuff would be necessary to build something like this. So we're trying to determine the surface area here. So we'll use our standard sort of approach. We'll chop up our interval into some pieces here. So we'll just imagine that we've got some arbitrary sort of pieces. As standard, we'll say that the width of each piece is delta x, and we'll take a look at some arbitrary piece, so maybe some x sub k or something like that, and we'll go up to that x sub k plus 1. So let's imagine we take a look just at this piece here. So there we go. And we'll sort of take a look at this little section here that gets revolved around to there. Okay. And we're going to cut that little part out. So, of course, what that sort of looks like is like a miniature version of the overall shape. And looks something like that. Okay. So, now, of course, this right here is not a particularly nice standard shape because, of course, this thing here is not a straight line. So let's try to understand this a little bit better. Let's imagine taking these sort of edges here and smoothing them out so they're actually a straight component. So let's go ahead and imagine sort of smoothing this out a little bit more. And we'll say that this should look roughly, if we sort of imagine a cylindrical sort of shape there. So what we're doing is, just to sort of make that a little bit more clear, let's give ourselves something like that. This process right here is we're going to sort of straighten out the curve. Why are we sort of building that cylindrical shape? Well, because a cylindrical shape, we should be able to sort of know from geometry a very easy sort of formula for the surface area of a cylindrical piece like that. So let's now sort of focus on the surface area of that cylindrical piece. So we'll take this down here and let's try to figure out the surface area. So what is the surface area of a cylindrical piece? Well, if you remember from geometry, the way you calculate the surface area is you take the circumference of the circle, so 2 pi r, and then you multiply it by the height. So this would be 2 pi r h, the surface area of that cylinder. And in that sort of description there, this right here would be the height, and the sort of distance here, that would be your radius. So your radius is measured like that. Because again, our cylinder is sort of on its side here. So we need to sort of understand that radius and that height in this sort of diagram here. So let's think about that radius. Well, if we sort of back up, the radius is this sort of distance. Now, of course, we smooth things out, so it's going to be a little bit bigger in our picture than that radius and a little smaller than that. But that should be based on some value of the function. So what we can say is we can say that the radius is going to be the function, the height of our function, based on some x sub k between that x sub k and that x sub k plus 1. So we'll say it's the function evaluated at some f sub k star. And that should be pretty clear. The radius is our function height, how far we are here from our axis of revolution. Okay, what about this height? Well, it might be tempting to say, well, the height is going to be that distance, delta x. But remember, we did this by straightening out this curve here. So if we straighten out that curve, that's not going to necessarily have the same length as this, because the curve is not a straight horizontal line. So instead, we want to understand the length of this piece of curve. But now we know how to do that based on what we learned in section 8.1 about the arc length. We can say that that height there is going to be roughly the arc length of this section because we're smoothing it out. So we can say that the height here is actually going to be the arc length. And for now, I'm just going to denote the arc length as L. So we now know that the radius is f of x sub k star, and the height is the arc length. So we can say that the surface area of this piece is 2 pi, the function evaluated at f sub k star, times the arc length. Now, what do we remember about the arc length? Well, we probably know all the way how to jump to the sort of integral expression for the arc length, but we're not quite there yet. So let's remember what we actually got for the sort of approximation of the arc length. Well, we did that as sort of a straight line distance approximation, and we said that it would turn out to be the square root of 1 plus the derivative at some x sub k star, squared. That was based on the mean value theorem, and then delta x, right? And we did that actually by first getting the arc length to be sort of delta x squared plus delta y squared, and then we factored out a delta x and went from there and used the mean value theorem. But this was the sort of expansion that we got. If that's a little unclear how we jump from here to here, you can go back and take a look back at 8.1 and just remember how we did that sort of approximation. So now we have this surface area expression. Is it exactly the surface area? Well, no, it's again only a rough approximation, but we can say that the overall surface area, what we're actually interested in, so the overall surface area is going to be roughly the sum over all these different x sub k stars of 2 pi f of x sub k star square root 1 plus the derivative at x sub k star squared delta x. And now we should be sort of very comfortable with this. We can say that the surface area is equal to the limit as delta x approaches 0 of the sum of these x sub k stars, 2 pi f of x sub k star square root 1 plus f prime f of x sub k star all squared delta x, which we can then convert into a definite integral. We can say that that is the integral. Since we're working dx, we could have chosen these x sub k stars anywhere from a to b. So our definite integral is going to be from a to b. 2 pi, our function, f of x, and then square root 1 plus the derivative of our function squared dx. So you'll notice that what we basically have is we have that arc length component here, which we're sort of used to from 8.1, and then we have this 2 pi f of x, which is coming from getting that 2 pi radius that's necessary for the surface area here. And it should make sense that there's a radius component now, because again, we're back, sorry about that, we're back to having a solid of revolution. So of course there's going to be a radius component because we're always going to be revolving around some axis here. So we now have that with this 2 pi f of x times the square root 1 plus f prime squared dx. So that's a surface area formula here. Okay, let's go ahead and summarize what we just did here and also talk about how we could do this with respect to y. Now, I don't mean going around a y-axis. I mean actually having the variable of integration with respect to y. So let's go ahead and talk about that. So, as a summary here, again, let's go ahead and just redraw our sort of visual and talk about what we just sort of discovered here. So, for right now, we're sort of assuming we have some continuous function like that. So going from a to b, and we're imagining that this is sort of y equals f of x. We're also going to imagine that the curve in terms of y goes from c to d. Okay, and we're revolving this curve around the x-axis. So we're going this way like we just did. And so, of course, we're getting something that sort of looks like that. And we're trying to measure the surface area of this resulting 3D shape. So what we just found is that the surface area of the resulting surface, or the resulting 3D shape, is given by this equation. Surface area is the integral from a to b, because you're working from here to here. 2 pi f of x, because the radius, if you're measuring this way, is the height of the function. And since we're working dx, the height is you plug into your function. And then square root 1 plus dy dx squared dx. Just going back to that sort of differential notation for the arc length, it's the same as saying 1 plus f prime of x squared square rooted, but just writing it with that dy dx notation. Okay, so this is just giving us exactly the result we derived on the previous page. Now, can we rephrase this result with respect to y? So not changing which axis we're going around, but changing the variable of integration. Well, if you imagine, we should be able to get this expression. The integral from c to d, because we're going to be now choosing our y values from here to here. 2 pi, instead of saying f of x, well, since we're working dy, we can say that the height is literally just y. And then square root 1 plus dx dy squared, because this expression here is how you do arc length with respect to y. So this gives us two alternate ways of determining the surface area if you revolve around the x-axis. If you want to work with respect to x, you'll use this one. If you want to work with respect to y, you'll use this one. In general, what I'd like you guys to sort of think about is that both of these two expressions are just two versions of the same formula. What we basically just figured out is that when we're revolving around the x-axis and we were trying to determine surface area, we can really think about it as this sort of general formula. The integral of 2 pi y, because the radius is always going to be the y distance, times the arc length. So you can think about how both of these expressions are just versions of this, one with dx and one with dy. Okay, so now we know how to determine the surface area of a solid of revolution. Let's go ahead and take a look at a couple examples before we talk about how to do this if we want to revolve around the y-axis. So let's go ahead and determine the surface area of a surface created by revolving the curve y equals square root 3x plus 1 from x equals 0 to x equals 5 around the x-axis. One thing I'd like you guys just to sort of pick up, if you cross-compare this sort of question with the questions we did back in Chapter 6, if you remember, whenever we did a solid of revolution and we wanted to know the volume, we not only had to describe the curve and the endpoints, but we also had to determine the region. And we had to say, was it the area under the curve or to the left of the curve? Because remember, to build an actual solid, to build something that has volume, you need to revolve an area. But we only want a surface area. So we don't have to talk about the inside of our shape. We just have to talk about the outside, the thing that determines the surface. So when talking about a surface area question, all you're going to be given as information is the curve, the bounds, and the axis. You don't need to talk about, is it the area under the curve, to the left? Doesn't matter, because we're just talking about the surface of the shape. So in general, since we're revolving around the x-axis, so surface area around x-axis, well, we just saw that the sort of general formula is the integral 2 pi y times the arc length. That's what this says right here. And that's really how I recommend thinking about it, and then we'll choose the appropriate one based on whether or not it's easier to work with respect to x or with respect to y. All right. Since we have everything in terms of x, it is probably easier to do this with respect to x. So let's do this. Let's do this with respect to x. So we'll have the surface area be the integral. The bounds will be 0 to 5. So 0 to 5. 2 pi. Instead of y, because we're working with respect to x, we will replace the y with square root 3x plus 1. So square root 3x plus 1. And then for the arc length, instead of just the arc length, we'll put 1 plus dy dx, so the derivative of y with respect to x, squared dx. Now, of course, we'll have to determine this, so we can sort of do that off to the side here. If we have y equals square root 3x plus 1, then dy dx will be 1/2 1 over the square root of 3x plus 1, because remember, this is really 3x plus 1 to the 1/2. So I'm dropping that 1/2 down. Then I'm subtracting 1, so I'm getting negative 1/2 as the exponent. That's why the square root of 3x plus 1 is in the denominator. And then times 3 for chain rule. So our dy dx here is going to be 3 over 2 root 3x plus 1. Okay, let's pop that in. So we now have that the surface area here is going to be the integral from 0 to 5, 2 pi, square root 3x plus 1, square root 1 plus, plug that stuff in, 3 over 2 root 3x plus 1, all squared, dx. All right, we can start simplifying. And we've got the integral from 0 to 5, 2 pi, square root 3x plus 1, square root 1 plus. Let's go ahead and actually square this. So it looks like we're going to get 9 over 4. And then when we square that 3x plus 1, looks like we're going to have 3x plus 1, because it's squaring that square root. And of course, we still have our dx out here. Now, this is pretty messy. We've got a square root, and then we've got another square root with a fractional expression. But remember, if you have two things inside of a square root, you can multiply them inside the square root. And if we distribute this 3x plus 1 in here, well, when it hits the 1, we're going to get 3x plus 1. But when this 3x plus 1 hits this, we're going to cancel that out. So we can get that the surface area here is the integral from 0 to 5, 2 pi, square root, 3x plus 1, that's multiplying this, and then plus 9 over 4. And that's multiplying this onto this whole term, canceling those out, and just getting 9 over 4 dx. Okay, still a little bit messy, but we can put some things together. We have the integral from 0 to 5, 2 pi, square root, 3x plus 13 over 4 dx. Now, we should be able to finish this up with just a simple u substitution. So let's do u equals 3x plus 13 over 4. That means du is going to be 3 dx, which means we are going to get a 1/3 du equals dx. We can also go ahead and change our bounds. We have x and u, so our original x bounds were 5 and 0. If we plug those in, plugging in 5, it looks like we get 15 plus 3 over 4. So that sounds like 73 over 4. And then when we plug in 0, we get 13 over 4. So our surface area then is now the integral from 13 over 4 to 73 over 4. Looks like we get a 2 pi over 3, and we get u to the 1/2 du. Okay, let's grab this real quick, and we'll finish it up on the next page. Okay, so if we go ahead and just paste that in, there we go. So now we can integrate. We get the surface area. When we integrate that, we're going to get a 3/2, so we need to multiply by 2/3. So 4 pi over 9, u to the 3/2, evaluated from 13 over 4 to 73 over 4. So the surface area here is 4 pi over 9, parentheses, 73 over 4 to the 3/2, minus 13 over 4 to the 3/2. And there we go. We've calculated the surface area of the resulting solid if we were to revolve that curve around the x-axis. So you can see here that sort of similar to arc length, you don't really need the visualization here because the Unlike solids of revolution with volumes, where you have to be very careful about, are you going to use cylindrical shells, are you going to use distant washers, what is the actual region you're looking at, this is defined entirely just by the curve and the bounds and the axis of revolution. So once we knew we were going around the x-axis, we used this expression for the surface area. Then, since our function and our bounds were all in terms of x, we decided to do this with respect to x. We changed from y to square root 3x plus 1, because that's what y is equivalent to, and we used the with respect to x definition of the arc length. Plugged everything in, got a pretty messy integral, did some simplifications, and then we're able to finish this up with a simple u substitution. If you want, you can try doing this with respect to y. So what you would need to do is you'd need to figure out the y bounds. The y bounds, if you plug in x equals 0, looks like it would be from y equals 1 to x equals 4, or sorry, to y equals 4. So you'd have an integral from 1 to 4, 2 pi y, but then for the arc length, you would have to invert this and then take the derivative. So it would be a bit messier to do it with respect to y. But if you do, it should be doable, and you should get the exact same final answer that we got here. All right, for now though, let's try another one. So let's determine the surface area of the surface created by revolving the curve x equals y squared from y equals 0 to y equals 2 around the x-axis. So once again, we have surface area around x-axis. So the general formula is that this is going to be the surface area is 2 pi y times the arc length. Notice at this time, the function and the bounds are in terms of y. So let's try to work with respect to y. So work with respect to y. So that means that the surface area is going to be the integral. This time the y bounds are 0 to 2. 2 pi, no need to replace this y, so we just leave it as literally a y. And then square root 1 plus dx dy, so the derivative of x with respect to y, squared dy. So we need to determine dx dy. Very easy to do that. It's just going to be 2y. So we'll need to plug this in here. So the surface area here is going to be the integral from 0 to 2, 2 pi y, square root 1 plus 2y squared dy. Let's just simplify inside a little bit and then figure out how we're going to integrate this. Integral 0 to 2, 2 pi y, square root 1 plus 4y squared dy. Whenever dealing with arc lengths and surface areas, you always have to think about how are you going to integrate this square root. Last time we just u-subbed for what was inside the square root because it was a linear term. This time that's a little bit riskier because if we do u equals 1 plus 4y squared, the du is going to be like 8y dy, so we need to make sure we have a y dy. But we do, so we can get away with another u substitution. So let's do u is 1 plus 4y squared. Du is going to be 8y dy. If we think about it, we really only have a y dy, so I guess we're going to get a factor of 1/8 when we do this. We'll need to go ahead and change our bounds. Our original y bounds were 2 and 0. Our new u bounds, well, if we plug in 2 there, 2 squared is 4 times 4 is 16 plus 1, that's going to be 17 and 1. So it's going to be from 1 to 17. So the surface area here looks like it's going to be the integral from 1 to 17. We get this factor of 1/8 that is going to cancel with the 2, so I guess we get 1/4 pi, and then we get u to the 1/2 du. Now it should be very nice and easy to integrate that. This is going to become a 3/2, and we're going to multiply this by 2/3. So it looks like we should get 1/6 pi u to the 3/2, evaluated from 1 to 17. So it looks like the surface area in this case is 1/6 pi times 17 to the 3/2 minus 1. So there we go. We determined another surface area for a given solid of revolution, or surface of revolution, since we're not worrying about what actually is filling up the inside. Okay, so why did we do these two examples? Well, the main idea is that both of these were ones where we went around the x-axis, but in one we chose to work with respect to x because everything was in terms of x. The other one we chose to work with respect to y. So it was around the same axis of revolution, which is why the main structure of the formula didn't change. We just chose a different variable of integration based on what was easiest for the information that was provided. All right, now we are ready to talk about what if you want to revolve around a vertical axis of revolution. We know how to deal with a horizontal axis of revolution. Let's talk about how to deal with a vertical one. So we're going to extend this to revolving around the y-axis. So we're not going to rederive the result, but we're just going to sort of try to do it visually here. So if we imagine now we're going to have our sort of curve set up there. Let's get that a little bit nicer of a line. So there's our curve, and again, let's sort of imagine that maybe that's from A to B, and this is going to be now from, say, C to D, but this time we're going to be revolving around this axis, the y-axis, or if you prefer, a vertical axis. So that's going to make sort of a shape that looks like that, and then, of course, it's a 3D shape. So what we're sort of making here is a bowl shape. And we're asking ourselves how much material would be necessary to construct this bowl. Back from chapter 6, we would know the volume of the bowl, how much stuff could we pour into it. But now we're talking about the surface area necessary to build it. Okay, so that's what we're sort of looking at here. Now again, we could do our same argument. We could try to slice up the sort of interval, maybe do it with respect to y, and sort of try to build those rectangular pieces, sort of like this, and then have this, and sort of revolve that around here, and then build sort of those little mini shapes. But we could also just sort of make sort of an argument here. Notice that once again, we're going to have that sort of surface, that arc length component. That arc length component is going to be important because, again, that's going to determine the sort of height of the piece when we revolve it around. And we're going to have a radius component. But notice that the radius component this time is going to be based not on y, but on x. It's going to be the horizontal distance from this axis to our curve. So it shouldn't be a big surprise that the surface area here can be given by this formula. The integral from a to b, 2 pi x, and then the arc length 1 plus dy dx squared dx. Or if you want to work dy, well, then you can't use x, you have to use the function in terms of y. So now we're actually thinking about this function as x equals g of y. And then, of course, if you do 2 pi g of y, you have to use the y version of the arc length, 1 plus dx dy squared dy. Once again, you can think about these two formulas as sort of two versions of a general formula. The surface area, if you revolve around the y-axis, is really 2 pi x times the arc length. So this is sort of the general formula I would try to remember here. Okay, so let's go ahead and take a look at some examples of this guy. So we want to determine the surface area of the surface created by revolving the curve y equals 1/2 x squared minus 1/4 ln x from x equals 0 to x equals 1 around the y-axis. So once again, we sort of want to make note, we have surface area around y-axis, which is what we were just talking about. That means that the surface area in general is going to be 2 pi x, because we're going to be measuring the x distance in terms of our radius, and then the arc length. Then we can choose, do we want to do the arc length with respect to x or with respect to y? Notice that since this is in terms of x and this is in terms of x, we'll go ahead and work with respect to x. So that means that the surface area is going to be the integral from 1 to 2 pi. Since we are working with respect to x, we can just leave that as x, so 2 pi x, and then square root 1 plus dy dx, derivative of y with respect to x, squared dx. So this is going to be us working with respect to x, because I really don't want to have to try to invert that. We can go ahead and get the derivative here, dy dx. Take that derivative, looks like we should get x minus 1 over 4, 1 over x. Because the derivative of that x squared, we drop the 2 down, and it'll cancel with the 1/2, and then here, derivative of ln x is 1 over x. So we can pop this in here. So it's going to be pretty messy. Well, when we first do this, we'll get that the surface area is the integral from 1 to 2 pi x square root 1 plus, and in here we'll have x minus 1/4 1 over x squared dx. All right, let's go ahead and expand this out first, because I don't really see anything else to sort of do, because this, we don't even know what's in here, so we can't even try like a U sub or anything. So if you want, you can do that sort of off to the side, or we'll just do it underneath here. Let's expand this thing. Let's give ourselves a nice color to do that in. So this right here, so x minus 1 over 4, 1 over x squared. Well, we did something sort of similar to this. We can think about this just as straight up FOIL. So we're multiplying like this. Okay. So if we take those first terms, it looks like we should get an x squared. Then the outer term, notice that the x is going to cancel with the 1 over x. So it looks like we're going to get a minus 1/4. Then those inner terms, same thing, another minus 1/4. And then those last terms, this times this, looks like we're going to get plus 1 over 16, 1 over x squared. And that looks like it simplifies to x squared minus a half plus 1 over 16, 1 over x squared. All right, let's pop that in and see if that makes anything any nicer. So we have the integral from 1 to 2, 2 pi x square root 1 plus, and now we have x squared minus a half plus 1 over 16, 1 over x squared dx. All right, now we talked a little bit about this to be on the lookout when you have that minus 1/2, because when you combine that with the 1, you're going to get the same expression, but with a positive cross term. So we're going to have 2 pi x square root x squared plus 1/2 plus 1 over 16, 1 over x squared. So this is going to be a perfect square of these two terms, but with positive constants there instead of the negative term. So that means our surface area is going to be the integral 1 to 2, 2 pi x square root x plus 1 over 4, 1 over x squared. Now we have a perfect square, so we can square root that square and cancel that out. And after all that, we now have that the surface area is from 1 to 2, 2 pi x, and we have x plus 1 over 4, 1 over x dx. Now we might be tempted to say, oh, everything's pretty simple, we can just go ahead and integrate, but this is still a product, so let's distribute this x in and get that the surface area is the integral from 1 to 2, 2 pi, and let's see, we get x squared plus 1/4 dx. So let's grab this, and we can go ahead and finish this up on the next page. Okay. Looks like we brought along a little miscellaneous one. Let's just get rid of that. Okay. So now we should be able to integrate this. This gives us that the surface area is really 2 pi, and then some parentheses. Integrating that x squared gives us 1/3 x cubed plus 1 over 4x, evaluated from 1 to 2. Plugging in, the surface area here is 2 pi, parentheses, another set of parentheses, looks like 8/3 plus 1/2 when we plug in the 2, minus 1/3 plus 1/4 when we plug in the 1. And there we go. There's our surface area when we revolve that curve around the y-axis. So key thing to recognize here is that since we were going around the y-axis, we used a different sort of general format for the surface area, 2 pi x times the arc length. Since everything was in terms of x, we decided to work with respect to x, which meant that this x here stayed as just an x, and in here we did the derivative with respect to x. And then this one turned out to be sort of one of those special cases where what was inside the square root could be recognized as a perfect square. We were able to eliminate the square root and then just sort of directly integrate. All right, let's wrap up this introduction to surface area. We still have some more things to say about surface area, but let's wrap up this introduction by taking a look at one more example where we're going to write down the integrals with respect to both x and y, even though we're not going to evaluate them. So we're going to consider the surface area created by revolving the curve y equals e to the x from x equals 0 to x equals 2 around the y-axis again. And we're going to try to write down two integrals, but we're not going to evaluate them for the surface area. So notice that again, we're doing surface area around the y-axis. So the sort of general form here is going to be the surface area is the integral 2 pi x times the arc length. Okay, so for A, it can be pretty straightforward. Since we're working with respect to x, bounds are going to be the x bounds, 0 to 2. 2 pi x, because the x can just stay an x since we're working with respect to x. And for the arc length, we're going to have to do square root 1 plus dy dx squared dx. So, since we have y equals e to the x, dy dx is going to also be e to the x. So we can pop that in there, and we should get that we have the integral from 0 to 2, 2 pi x square root 1 plus e to the x squared dx. And there we go. That's going to be the surface area. We're not going to evaluate that, but this would be the surface area going around the y-axis with respect to x. All right, now let's try the second part, which is we're going to with respect to y. So first we need to figure out the bounds. Since we're going from x equals 0 to x equals 2, plugging those in, e to the 0 is going to be 1. E to the 2 is going to just be e squared. So our new bounds are going to be from 1 to e squared. Now we would say 2 pi. We can't say x though, because we're trying to work with respect to y. So we need to invert this. Notice that if we do invert this, we can say if y equals e to the x, then x equals ln y. So instead of saying x, we're going to say natural log of y. So we will put natural log of y square root 1 plus dx dy squared dy. So now this is the same surface area. If we were actually to evaluate it, it would be the same as what we did here, but just with respect to a different variable. Last thing we want to do is actually replace this dx dy. Well, that would be differentiating here. And you can see that that would give us dx dy is equal to 1 over y. So we throw that in there, and we get that we would use the integral from 1 to e squared, 2 pi ln y square root 1 plus 1 over y squared dy. If you were to evaluate these, or if you used a calculator or a computer algebra system to evaluate these, what you get here is exactly the same as what you get here. Because again, these are not different surfaces. They're the same surface. One is we're just working with respect to x. One is that we're working with respect to y. If we decided to revolve this around a different axis, like the x-axis, then we would get different surface areas, because that would be a different surface. Revolving y equals e to the x, something that looks like this, around the y-axis gives us sort of a bowl shape like this. But going around the x-axis would give us something that looks like that. That's definitely not the same shape. So being around a different axis changes the surface you're looking at. Changing the variable just gives you a different expression, but for the same surface area. All right. In the next video, we'll finish up section 8.2 by connecting what we've been doing here with solids of revolution and sort of revisiting all of the geometric things that we've learned how to analyze thus far.